Okay, mes amis, this is Roger once again. Can I upend physics in under 15 minutes? And I say yes, I can. What are neutrinos and how can we measure their mass? The weirdest subatomic particles require enormous equipment to study. I do not agree with that. And they say that this is one of the most misunderstood particles there are. Theoretical physicists still know remarkably little about neutrinos, despite the fact they've been aware of existence for nearly a century. Well, I know everything about them, and I'll show them to you right now. Okay, so you say, Roger, that is a very bombastic statement that I know about neutrinos. However, it happens to be true. Muon and electron neutrinos and the showers of electrons are caused by electron neutrinos. Muons just go about their business. Let me explain how we got to these points, exactly what CERN wants to see. Just in case you missed it, muon neutrinos and electron neutrinos are black and white balls. I'll show you in a minute. The muon neutrino separates, the muon just goes on its way, and it no longer is really a neutrino. The electron neutrino becomes a shower. That's exactly what you have, the black balls separated. Now, prior to them separating, they were in photons. These are photons of light. Not particles smashed from protons. These are photons of light, literally the smallest particles that exist. And Fermilab agrees with that. There they are right there. Fermilab point particles. This one here, the black one, is just a fixed particle. That one's a little glowy one. It's exactly what they are. They're right. And we're seeing them, though, from light research. This is not smashing gigantic particles and digging through debris. We can see these actually focus right here. That's the light coming in. And if we can make it hit exactly dead nuts into the venturi, you have a nuclear explosion. And that is really a subatomic nuclear explosion. The particles have fission here and fusion back here. In between, raw energy. And here it is right here. Fission, fusion. If you can explain it in any other way, I would like to hear it. Now, what are neutrinos? Well, here they are. The black one and the white one are neutrinos. And they go into showers and the sterile muon. Precisely what I showed you. Not only that, there's a third neutrino called a tau. We see that too. Okay, I'm going to try to explain this. They say that there's 3 flavors of ice cream. They go and they get ice cream, they buy it as vanilla. By the time they get home, it turns into chocolate. And when they put it in a bowl and go in the other room, it turns into strawberry. So it's 3 different types of neutrinos. Well, that's not true. There's only 2 different types of neutrinos. There's the black one and the white one. And the third one, the tau neutrino, is 2 blacks with 1 white. You see it? 2 blacks, 1 white. Over at the venturi, all you have is black and white. So you have a muon neutrino is the black one, and the electron neutrino is the white one. Well, when you turn them into photons, you have 1 of each. So this is 2 blacks and a white. That's 1 weight. This one, a white, weighs almost nothing. The black weighs a lot compared to the white. And then you have photons, which are just 50-50. So you have 2 whites and 2 blacks. But the black is almost 95.35, I believe it is. Yeah, 95.35% of the mass weight. If you go to Yale Quantum Physics, which I did, you will see that the first thing the professor comes out, he says, nobody understands quantum physics, so you just listen to me say what I say and everybody will be happy. Then you won't understand it either. In a week, you won't understand it just as he doesn't understand it. He says Feynman doesn't either. Feynman was the guy that wrote all of these equations. He says, if you think you understand quantum mechanics, you don't understand it. This view is widely held in public. Quantum physics is supposedly impossible to understand, including by physicists. And that's true, it isn't, because it isn't right. Okay, my friends, this is going to be really fun because she's explaining them exactly the way the standard model is portrayed, and I'm going to show you. I can see these particles and I can tell you how they manifest themselves and why they have these different weights. Okay, and this is Kirsty Duffy, who I have not been able to contact. I've tried over and over and over, and on LinkedIn, they won't respond. This is Fermilab, and I have the particles they're looking for. Now, they're talking about the standard model. Now, listen to this.
One of the groups of particles in the standard model is the leptons, home to our trusty neutrinos.
Okay, those are the neutrinos that I just showed you or will show you. Okay, she's saying that there's all these different particles, and she's starting off with the electron neutrino, muon neutrino, and tau neutrino. I say that's all that exists is these two. And this is nothing more than two blacks and one white. I will show these. These are their mass units. And I've calculated out that muons weigh 95.65, I believe it is, 95.65, something like that. It's over 95% of the weight of the particle, which is these two together make the particle, the white and the black. This just has an additional black, and that accounts for something that really always bothered me, is where the extra blacks came in after the white went through the venturi. How did they end up getting the blacks back together if everybody else had one? They were all paired up already. But I could see they were coming back and attaching to the red. Okay, now I'm going to let Kirsty keep going. She says they're starting out with the leptons, home to our trusty neutrinos.
Also in the lepton group is the electron, powering the device you're watching this on.
The electron is nothing more than one of the glowy ones attached to the black one. That's all it is. They call them gluons too.
And two similar but heavier particles, the muon and the tau.
Alright, and I showed you what the muon is. That's that black ball. The tau is the two blacks and one white. These are the two heavier ones. The glowy one, the electron neutrino, weighs virtually nothing.
Since all of these particles are tiny, the idea of one being heavier can be pretty abstract. But if we scaled an electron up so it had the mass of a mouse, the muon would be like a cat, and the tau would be a kangaroo.
Alright, and that's exactly what I would say too. The electron has almost no mass whatsoever. It burns like hell. It's got a huge field that pushes and shoves, but that's it. It's just an expansive field. There's nothing really to it hardly. But it does have some form of a weight inside, tiny as it is. But it's very, very pushy. Then you could go out to the muon, that black ball. Then they go to the tau, which these are not correct. It's 0.7 ounces, 140 ounces, 2,200 ounces. No, this would be 0.7 ounce. I can go with that. 140 ounce, But now you got two muons and one electron, so that should be 280 and 281.4. That's what I say. This twice, that once. Not that big gigantic thing.
Side note, this trifecta of different generations of particles is one of the big questions in physics. Why are there three similar versions of an electron rather than...
See, it just doesn't work. I'm not going to bother going on about it, but the Higgs is a product of these. Remember I talked about, they're talking about a Z boson. Let me take these closed caption on. You got the white and the black ball. That's it. Case closed, the white and the black ball. Then a gluon is just those two together as a gluon, which is actually an electron. Two gluons back to back as bar magnets make a photon. Case closed, that's it. When these two crash together, they make Higgs. All of this is built into these already. I've shown this a million times. I'll show you these, well, I probably already did, but I'll show you again. The W and the Z bosons, the black and the white. The gluon is the two of them together. The photon is two gluons together. The Higgs comes as these two come back together, the neutrinos. So if you want to see this article about this Fermilab, it's called What's the Point? It's by Don Lincoln. He works with Kirsty Duffy, and they do all of the muons and so forth. And I'd love to discuss it with them, but I think I've shown the particles that we're looking for right here. And not only that, we can see them, and we can actually squirt them onto a substrate. What happens with them is they smash these huge particles together, protons and neutrons, all kinds of things, and they just get debris. And they've seen these, but we can see them actually manifest, and then we can see them separate, and then we can see them come back together. So here they are turned into photons. Normally don't see that. You have to be coming into the accelerator here. This is our accelerator. And an accelerator is rated for efficiency by the increase in luminosity. And there was virtually nothing here until it started to accelerate, and that is luminous as hell. And this, I showed you, is the two particles together, the black and the whites together, which made a photon. Right here, that's a photon, and that's just the energetic values of this. We can see that this one, as I showed you, can get big and it can get small. That never changes, never changes. So when we put it into our venturi, which is a very, very thin slit, and forced everything to go around these corners and into that slit, they all smash together and push the black ones back out. And here's what happened right here. There it is. Here it comes down. They have to accelerate. Here's the key. Light is not supposed to accelerate. Well, that's not correct. It does accelerate. And this is the acceleration phase right here. You see it pulling itself out of the magnetic wave? It should never leave that wave. Well, it's being accelerated because that's what a venturi does. However, here's the key. Right here, it's experiencing what's called reverse EMF. That stands for reverse electromotive force. Push, 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 push. Can I show that? Absolutely. This is unbelievable amount of energetic luminosity. It's even making all of these particles that you never see before start to glow because they're being pushed back against. Not that they're pushing hard this way, they're being pushed back against. That is a nuclear explosion. And that, my friends, right there is fission, where they come apart, and that is fusion. And this is, it's so energetic you can't even see the venturi. But the venturi comes this way and this way into a little tiny slit right here, just a single slit. And the black can't get through. It goes around. Now remember I said that the black in the tau being two blacks and one white? This pretty much solves a lot of the stuff I was worried about. It appears that taus might be just laying around because somehow these white ones, they're 100% white here. They left the black ones back here. That's what I'm seeing. I don't know if you've seen anything different. You think this jumped over here? I don't think so. I think this came through white and it found some new black ones over here to attach to. Almost instantly. As it came through the air, I'll show you the Higgs fields, and you can actually see the black, the whites wrapping around the blacks to start to grab it in to become a particle. I'll show you that. So don't forget, here's the acceleration. And then we're going to see one flavor of the neutrino, which is the tau. Then we're going to see the photon. Then we're going to see the split, which is the muon and the electron neutrino. So we have the tau, then a photon will show up, and then the muon and electron neutrino. And then on top of that, we created the showers. So we're even beyond that, and we created the showers just like they wanted, and then we should be able to put a harvest device right in there to create free energy. I don't see why not. If somebody could tell me why that shouldn't work, I'd like to know why. If this is increased energy, which is power, whenever you see luminosity, it's energy. Whenever you see luminosity more than you started with, it means you increase the energy. That's just, there's no other way to take it. This wasn't as energetic as it is here. We did absolutely nothing to this light other than put it through our venturi. It takes nothing. It just sits there and eventually goes through the venturi, forces its fields to crash, just like they're doing at CERN. Only at CERN and Fermilab, they're trying to hit head on. Well, they don't like to hit head on. They go this way, they go that way, they go this way. They only get in a couple hundred collisions every now and then. It's nothing like we have. We get thousands and millions of them a second. Right here. And we can do this all day long. It's not, there's no bang and it's over. Let's analyze it. It's until the cows come home. And even if they never come home, it's still going. Well, just so we can get to the end of this, remember I said that's the tau neutrino. It's got more weight than the ball, each ball by themselves, the black and the white. Glued together, they are photons. Now, the reason they take on different weights is because they're banging up against each other. Boom, 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 boom. Now, coming into our atmosphere, all right, you should be able to understand it now. That's what I call the tau, and that has a certain weight. This is the photon, which is two gluons. The black and white is what's called a gluon. I call it an electron. Back to back, it's a photon. When they hit at the venturi, they separate and become the black and white particle, the muon and the electron neutrino. So just to put it all in perspective, this is the new model. It's dipole, because everything's a dipole. Dipole electron flood theory. Now, we did make a monopole. Nobody's ever done that before either. And the monopole is that single white ball, which I showed you, and the black ball. Those are monopoles. One is one side and one is the other side. They're separated. Now, remember I said an electron is not just a glowy little electron. It's these two particles, the black and the white together. And these are the neutrinos. I think I've been pretty clear about that. Once they're glued together, they're called a gluon. In my case, I call them electrons, which that's what they are. These are the things that flow. They're heat, they're electricity, they're lightning, they're static. Photons, different story. This has only got one glowy end. It wants to burn into something. This has a surrounding field. It bounces. These bounce off. That's why you see bounce packets. You see them as light. Tau neutrino is this, and that is stacked up just before it turns into a photon, and then the photon explodes into particles. All right, once again, this is not my drawing. This is CERN, Fermilab. It's muon neutrino is the black ball. Electron neutrino was a white ball. That turns into showers. And because it's showering electrons, to me that means we're pushing a whole lot of excess electrons. To me, that's an increase in energy. To me, that's free energy. All right, I showed you all the particles. We started with that. We increased it to this enormous luminosity, which means that our particle accelerator is very, very efficient. We created Higgs fields coming out of the particle accelerator. When they recombine, you see the black is recombining with the white. That's the tips. That's the tips of these fields. The black is recombining with the white. It's amazing. I can't. And the back here, it hasn't caught up with the black yet. These are the Higgs fields. These are these spinning particle fields. And I have a lot more on this, a lot more. Starting to get into the dipole fields in space. Everything's a dipole. If it's spinning, it's a dipole. Case closed. The moon's not a dipole. It's not spinning. This is a planet. I believe this is Venus. And I can tell you why, because it has a double field. That's one field, and it has a second field. That's not standard by any means. And also we have this one here. This is Dylan. Well, no, Dylan didn't do this one. This is the Russians in space. That's a black hole they created in space. We now know that the black can separate from the white. In zero gravity, they can move, so they push all the black in the center and the white surrounds it. Basically like a planet in space with all the white particles, which is trying to get attracted to the Earth or whatever planet it was. All right, it appears that the central core takes on the more dark matter. We know that for a fact these electrons will zzz right to Earth. Zzz, electricity. It's Earth ground. Well, why? I know why. Because the black wants the white. It has to have more black in the center. That's the only way I can see it. And the other thing that tells me that there is likely more black than white is here's the particle coming in. We know at this point it's a photon. 2 blacks, 2 whites, and I assume that's where they all are. But here we know we separated them. The black separated from the white. As of that, there is no question whatsoever. None. Zero. And they talk about it. The muon gets parted from the electron shower. That's exactly what you see here. Now, over here, they come back together. And the blacks attach to the whites. And this is where you start seeing the Higgs field start showing up. We were standing like here looking in, and you could see the Higgs on the outside. But we were in with the cell phone here looking right into there. And the reason we can see it with the cell phones is because of luminosity. Just start doing a little research. You find out it's the exact same thing they're using. CMOS technology, same thing they're using at CERN, Fermilab, no difference whatsoever. It's just that ours is a little less expensive. Now, this is where we see the Higgs fields coming back together. So where do these black particles come from? If everybody's got to have a black particle, how does this happen? Also, by the way, these are not interference patterns because of a wave flapping this way and another wave crossing over it. This is a single slit. This is the way particles go. It's a right-hand spin. It spins this way. When they hit the venturi, some go off to this direction, some come over the top and come out this direction. They're all over here. And they're coming down, and it forces these fields in. And there's a very tight restriction here. And there's like a funnel. And the blacks can't get through. They just can't make it. They're just solid big balls of matter that just can't get through. However, I believe because of the pulsation, it's squirting these through like extreme powers. Now, when they come out the other side, they're spinning off this way, they're spinning off this way. It doesn't matter. They'll set up their own lines because they don't want anybody next to them, they don't want any next to them. So they'll make a strip going this way and this way and this way and this way, all separated the best they can away from each other because they don't like to be next to each other. The white is explosive. The black doesn't care. The black will go right on top of itself. They just glob right together. They are the attractive force. They're gravity and they're dark matter. And nobody's ever seen them before because they didn't realize they were attached to what they always thought was an electron. The last picture, CERN, Fermilab, and them, now they smash together here and they just have piles of debris and they dig through it and they find these tiny particles, the black and the white. They have no idea where they came from. You can see we can squirt those right onto a substrate. And I believe using something very simple like that, basically harvesting the solar effect of what we did. We separated. This is nothing more than like light, only this is light on steroids. Light coming from the sun is just hitting these solar panels and forcing electrons to drive through. Well, we're putting them on, really forcing them. We're forcing them. That is an absolutely enormous amount of increase in energy. So it could be that we're increasing it 200 times. And it might even be more than that. But let's go with 200. If we needed 100 to keep this thing working, we still got 100 to go. So, or half of the energy. Anyway, just so you understand, we are not using gigantic particles because every one of these is all of this. It's 1,836 of these electrons. We're using these. This is what we smashed through here. Boom, just like that. Boom, and then it broke apart.